So I figured I would start with that. So this should look familiar to those who have done their lab report on titrations. I just sent out a announcement about lab reports because they're sort of getting kind of late. So this is one that's in your lab report. And sort of, it's a good question because it goes over a lot of the stuff we've been talking about. Weak acids, weak acids, strong base, titration. So it's very, very similar to the actual lab, where our weak acid was acetic acid. So this question is about an unknown weak acid. I think that sort of threw some people because they sort of expected that they would get a pKa of around 4.7 for acetic acid, but this isn't acetic acid. So for this sort of question, how do we start? What's like the very first thing we want to do? Sorry?
Is that balance the equation?
Yeah, that's a great place to start. Make sure that the equation is balanced. Because remember the sort of evil question I had before about a diprotic acid. A diprotic acid is something that has two hydrogens and an anion. So when that is titrated, that takes two hydroxide ions and makes, oh, wrong place. That takes two hydroxide ions to titrate both of those protons, H plus, and you get 2 moles of water. In this particular example, our weak acid seems to have a single proton, and the anion, what's the conjugate base in this particular, for this weak acid?
NAA?
Yeah, it's just A minus, basically. That's the conjugate base. And so it's all 1 to 1 to 1 to 1. So yeah, so we're good to go. So that's a balanced equation. So we got that. So where do we calculate two things. We need to calculate the molarity of the weak acid, and we also need to figure out what its pKa is. How are we going to figure out what its molarity is?
The molarity of sodium hydroxide.
Right, so that's what a titration is, right? We take a concentration of something that's known, and then we figure out what the concentration is of something that's unknown. So our concentration of base is 0.413 molar. And since this is a 1 to 1 to 1 ratio, we can go ahead and say the concentration of acid times the volume of acid is going to equal the concentration of base times the volume of base. So we know what this is. What's our volume of base?
$31.25 mils.
That's right, because that's the end point. And the end, what does it mean when the end point is achieved? What does that mean? How do we know we've reached the end point? We're doing a titration. How do we know the end point has actually taken place? We've reached
Color change.
the color change, right? And when does the color change? When do we see that big increase in pH and then the color changes?
Was it halfway?
Halfway, what halfway to what?
I just remember it being like somewhere like halfway to the endpoint.
No, we're actually talking about the endpoint right now.
Oh,
When
okay.
does that take place? So we know it takes place when the color changes, and we know the color changes when the pH increases, but why does the pH suddenly increase at the endpoint?
Is it like that maybe the pH changes from like an acid to a basic, or maybe
It
the
does.
basic to an
Why does it do
acid?
that? Right, it goes from an acid pH to a basic pH, but why?
Does it have something to do with the midpoint? Oh, no, sorry, someone else said that.
Nope. So remember when we looked at a graph where the pH, so this is our pH,
The equivalent point, I believe.
and this was the amount of hydroxide added. And then we saw the sort of went like this. Sort of went slowly up, and then all of a sudden, suddenly went up dramatically. What happens there? At that volume of hydroxide, what happens? Or why does it increase suddenly like that?
Is it the equivalence point?
It is the equivalence point. The equivalence point is where this actually happens. And the end point is when we see it happen. We try and make the end point as close to the equivalence point as possible. So what's equivalent at the equivalence point? Why is it called that?
The amount of base and acid.
Now that is a tricky question. So does that
The
mean
moles.
is it moles of acid? Is it moles of H plus? Is it moles of, what is it exactly? Moles, you're right, but moles of what precisely?
H plus and the A minus or
OH minus, yeah.
OH minus.
It's when moles of hydroxide equal moles of H plus. And if that is from a weak acid that only has one proton, that should also be the number of moles of the weak acid. So at that point, that's why this equation works. Because concentration is in moles per liter, volume is in liters. So what we're basically saying here is that moles of acid on this side equal moles of base on this side. So it's moles. That's the equivalence point for the moles of H plus and OH minus are the same. So we know what our concentration of base is. We know what our volume of base is. So our volume of base is 31.25 mils. What is our volume of acid?
Is that the 25.0 milliliters?
What does analyte mean? What does this mean? Analyte. What is an analyte?
The thing that's being identified and measured.
Right, it's the thing that's being analyzed. That's the easiest way to remember it for me. It's being analyzed, and we're analyzing the acid. So yeah, it's 25 mils is the volume of the analyte or volume of the acid. So that's 25.0 mils. So now we pretty much have everything we need to figure out the molarity. So we want the concentration of acid. That's going to be the concentration of base times the volume of base. There's our volume of base. And we don't even need to change the units as long as we're using the same units of volume for each. If we need to figure out the number of moles, then we do need to change the units to liters. But in this instance, we don't, because we're just going to cancel units anyway. So the unit volume of base is 31.25 mils. And we're going to divide that by our volume of acid, which is 25.0 mils. So what's our concentration of acid? So you can see that the mils cancel out. And we're left, and the unit we're left with is molar. So that's what we want. We're left with a unit of molarity. That's what
You
we
get 0.516 molars of
6 molar. There you go. So that's our molarity. And that makes sense because we had less of a volume of acid and a greater volume of base. So that would mean that the concentration of base would be less than the concentration of the acid. And you can see that it is by a little bit. So 0.516 molar. So we got the first part. Now the second part's where it gets tricky. So the second part of the information we have is that this is what the pH was around midway or so. And the thing is, it doesn't need to be midway. We could have the pH reading anywhere. And you can see that this actually isn't midway, because if the end point was at around 31 mils, midway would be around a little over 15.5 mils, but this is less. So that's less than midway. The reason why we normally pick midway, because at that point, half of the acid has been converted to conjugate base. And at that point, the concentration of the acid should equal approximately the concentration of conjugate base. And that's important because of our old friend, the Henderson-Hasselbalch equation, which says pH equals pKa plus the log of the concentration of the conjugate base divided by the concentration of the acid. And when the acid and the conjugate base equal each other, that is log of 1, and that equals 0. So at that point, the pH is approximately equal to the pKa. It's a good way of estimating what the pKa is. Go back and see about halfway to the equivalence point what the pH was. But we're not halfway this time. So what we're going to have to do is actually calculate what is our amount of conjugate base and our amount of weak acid. So how are we going to do that? How do we figure out how much conjugate base and acid we have at this point? So look at our equation. HA gets consumed and converted into A minus. So the more base we add, the more hydroxide we add, the more acid turns into the conjugate base. So how are we going to calculate the amounts of acid and conjugate base at that point? Where should we start? I'll give you a suggestion. We can start with how many moles of weak acid were there at the beginning. before I added any hydroxide. How could I figure that out?
Concentration and volume.
Right, because we just calculated what the concentration was, and we know what the volume is. So that'll give us the number of moles of HA at the beginning. So what was our new concentration was, what, 516, was it?
0.51625, but yeah, 0.516.
516, yes, you might as well use all the digits till you get to the end. That's one thing I've noticed about people's lab reports is a common mistake people are making is that they're rounding their numbers and then they're doing calculations with rounded numbers, and that's a bad idea. So don't do that. So if you can carry 5 or 6 digits on your calculator, just go right ahead and do that. So that's our volume of weak acid, and we had 25 mils of the acid. And we can either convert it here or you can convert it somewhere else. But we want to convert mils to liters because this is in liters. So now we actually do have to convert milliliters to liters. Times 1 liter over 1,000 mils, 1,000 milliliters, cancel out milliliters, cancel out liters, and we're left with moles. So how many moles is that?
I got a 0.0129.
0.012. I got 0.01291, but
06, yeah.
okay. So that's how many moles of HA there were at the beginning. So that's going to be important because it will tell us how many moles were left after we added 13 mils. So that's what I had at the beginning. So I'll just write down the beginning. Beginning. So how many moles of HA am I going to have after I've added 13 mils of hydroxide? How am I going to determine that? So think of it this way. After you've added hydroxide, what happens to the number of moles of HA, your weak acid? What happens to the number of moles of them?
Increases.
It increases. Look at our balanced equation. So here I've got my weak acid. Here I've got my hydroxide. When I add them together, this is what I get out the other end. So as I add hydroxide, do I get more HA or do I get less?
I mean less.
I get less, right? It's actually consuming, the hydroxide consumes this on a 1 mole to 1 mole basis, as you can see from the balanced equation. So if that's the case, how many moles of HA will have been consumed after 13 mils of 0.413 molar hydroxide have been added? How am I going to figure that out?
We can use the pH.
What am I going to do with the pH? pH just tells me what the concentration of H plus is. I mean, you're right, I could figure out what the concentration. So if I figure out what the concentration of H plus is, then where am I going to go from there? See, the problem is there's two sources of H plus. One of them is the weak acid. The other one is the water it's dissolved in. So without the pKa, I have no idea of knowing what my concentration of HA is based on the pH, because I don't know what the pKa is. So the pH really isn't going to help me right here. Let's ask it another way. So I need to figure out two things. I need to figure out how much conjugate base is there, as well as how much weak acid is left. How would I figure out how much conjugate base is present at this point? Look at the balanced equation again. And remember, it's a 1 to 1 to 1 to 1 ratio.
Oh, it's
how
the
the-
same.
Hmm?
It's the same.
What's the same?
The moles of HA is the same as the moles of A, the moles of sodium hydroxide.
That's it. The number of moles of A minus are the same as the moles of hydroxide. That's right. Because for every mole of sodium hydroxide I add, for every 1 mole of hydroxide I add, I convert 1 mole of HA to A minus. So if I can figure out how many moles of hydroxide were added at that point, that's going to also equal the number of moles of A minus that are present at that moment, because it's a 1 to 1 to 1 ratio. So how do I figure out how many moles of hydroxide are present when there's 13 mils of 0.413 molarity hydroxide added?
Multiply
What do I multiply?
the concentration of NaOH
By
with
what?
the volume of
What volume?
13 ml.
Right, the volume, that's because that's the volume of the hydroxide that was added. That's correct. So that's going to be equal to 0.413 moles per liter times 13 mils times 1 liter over 1,000 mils. And liters cancel, mils cancel, and we're left with moles. So that's what we want. So how many moles is that?
I got a 0.005369 moles.
5369. Yeah, that's what I got too. 5369 moles. So that is the number of moles of the conjugate base that are present at this point right here. So we're sort of halfway home.
Professor, could you put that part back up? I wasn't
Oh.
following.
Sure. No, it's going to take me a while.
Uh-oh. Well, I know it is 0.413 moles times
13 mils. So the concentration is 0.413 moles per liter.
Right.
Then we multiply that by 13 mils.
Okay.
And then we multiply that by 1 liter over 1,000 mils.
Got it. Okay.
So that cancels our liters, that cancels our mils, and it leaves us with moles.
Got it. Thank you.
All right, no worries. So I
Wait,
have
Professor?
my moles of conjugate base.
Professor,
but-
sorry, question for you. So so what you put there, moles of OH negative is equal to moles of A negative.
Mhm.
And so because of that, we're taking the
So
the mole.
look at the equation.
Uh-huh.
Always go to the balanced equation. It'll sort of help you what's going on. So at the beginning, in the beginning, there was our weak acid. And we figured out how much weak acid there was by figuring out the endpoint was achieved, or the equivalence point. This is as close to we can get as at the endpoint. That's achieved when our moles of acid, H plus, and moles of base, OH minus, are equal. So that was achieved when that much base had been added. So we figured out with that much base at this concentration, that's how many moles of weak acid there must have been there at the beginning. But remember, according to the equation, every time I add a molecule of hydroxide, it removes a molecule of weak acid and creates a molecule of A minus. That's what that is. NaA is Na plus A minus. So it's like when we did our acetic acid titration, it was sodium acetate. If we titrated HCl, hydrochloric acid, we would get sodium chloride. So it's whatever, this is the conjugate base, whatever was attached to the H plus at the beginning. So every time we add a molecule of OH minus, we create a mole of A minus, or a molecule of A minus as well. So however many moles of hydroxide we've added to this reaction, we've created the same number of moles of A minus. That's where the A minus comes from. Okay, does that make sense?
Yes, that does. Thank you.
All right, cool. But what you have to remember now is that for every mole of A minus that's created, where did that come from?
The weak acid.
It comes from the weak acid, right? So every time we create, a molecule of A minus, we remove a molecule of HA, because that's where it's coming from. So how am I going to figure out how many moles of HA I have at that point? So if I've created this much conjugate base, how do I figure out how many moles of weak acid do I have left? Is it the same amount? Because it's a 1-to-1-to-1 ratio. That's pretty much the last piece of information I need, is the number of moles of the weak acid. I know how many was there at the beginning. It's this. I know how many moles of the weak acid have been turned into A minus. That is that number. So how do I figure out how many are left?
You
We
just subtract
subtract it.
You subtract them, exactly. Yeah, that's I love the overthinking. Yeah, I have this much at the beginning and I take some of it away. Well, I subtract to see how much is left. Exactly right. So that is just going to be, and these small numbers are confusing. It's really easy to make a mistake with these small numbers because it's really easy to put one too many zeros in or not enough zeros in. So I'll try not to make a mistake here, but that's 0.01291 minus 0.005369. That's the number of moles I should have left. So how many is that?
seven, five, four, one.
7541, that's right. 7541 moles of HA. Now we pretty much have everything we need because I now know how many moles of weak acid I have at that point. I know how many moles of conjugate base I have at that point. I know what the pH is at that point. Now I have everything I need to figure out what the pKa is. And why is that? Because of the good old Henderson-Hasselbalch equation, which I'm sure some of you are going to get tattooed on your arms at the end of the class. So we remember, hopefully, that that is pH equals pKa plus log of A minus over HA. Now in the Henderson-Hasselbalch equation, this is given concentration, but we don't need to calculate the concentration. Why don't we need to calculate the concentration? What's the ratio of the concentrations equal to?
Moles per liter.
Well, that's what concentration is. So if I have moles over liters divided by moles over liters and I have the same number of liters, then it's just a moles over moles. It's the same ratio as the moles over moles because this reaction is taking place in the same volume. I'm not doing it in two separate volumes. It's happening in the same volume. So I can just cancel the volumes. And that saves me a whole lot of pain trying to do even more calculations. So what we can do, instead of figuring out what the concentrations are, we can just use moles of A minus and HA, which we've already calculated.
Now, can you do this with all these type of examples? You just use the moles and not the liters?
If it's a ratio of molarities, then that's also going to be the ratio of the number of moles, provided that your volumes are the same. And here the volumes are the same. They're both in 25 mils plus 13 mils. They're both in the same 38 milliliter sample. So if the volumes are the same, then yeah, you don't have to figure out what the concentrations are. If they're different volumes, then no, you can't do that. But in this instance, we can. Is that clear to everybody? Right. I mean, we can calculate the concentrations if you want. It just means more pain and agony. We don't have to do that.
Professor, can
Yes.
you put in the chat that the website with the calculator that you recommended for log
Oh,
again?
right. Good point.
Thank you.
How am I going to do that while I'm sharing? I'll just stop temporarily. Yeah, so I've got it open actually because I was using it this afternoon. There it is. There it is. All right. Oh no. Do we actually lose all of the?
Sorry.
Oh no. Okay. Anyway, let's go back. I didn't think it would do that actually. Oh, damn it. Stupid computer. Oh wait, I think I know how to do it. Oh. Nah, it didn't work. Okay. To review. We had we had 0.005369 moles of A minus, and we had 0.007541 moles of HA. And our equation is pH equals pKa plus log A minus divided by HA. So I just explained that in the Henderson-Hasselbalch equation, A minus and HA are given as concentrations. But the ratio of moles over liters divided by moles over liters is just moles over moles because the liters are the same. So all we need is the ratio of moles and moles. And that's what we have. We have that. We have those numbers here. So we can just go right ahead and plug those bad boys in. So that's going to be log of 0.005369 over 0.007541. And that ratio is 0.7134. So you want the log of 0.7134. So what's that? Basically what you're asking here is what is 10 to the x equals 0.7134, and you're solving for x. So what's the log of 0.7134? Should be a number pretty close to 1. I mean, I'm sorry, pretty close to 0, because 10 to the 0 equals 1. And we're pretty close to 1 here.
I got a negative, Professor.
Yeah, you
Negative-
should, because it's
Uh,
less than 1.
Negative 0.14666.
Okay. So this is negative 0.147. So the pH was 3.65.
Sorry, for the A minus the moles, what you wrote previously was 0.005356 instead of 69.
Really?
That's what I wrote.
Oh, I have 5. I did it this afternoon. I had 5369 written down here, but
Oh,
it's going to be pretty close.
okay.
Yeah, I mean, so now, what's our pKa?
3.797.
And is that our final answer? Have a look and see how many significant digits were in the pH that you were given.
Should be 3. 360.
Exactly. Yeah, you were originally given 3.65. So your answer should have 3 significant digits as well. So what do we round this to?
3.80.
Right. So there's our 3 significant digits. This rounds up to 3.80. So that's how you do that. So another question I got was, what do we do after we've added more base than acid? And so what we could do with that, so a similar type question that confused people was, so if the endpoint was achieved when that much sodium hydroxide was added, what would the pH be when 35 mils of hydroxide have been added? How would we do that? What happens after all of the sodium hydroxide, all of the weak acid has been consumed? So after the endpoint, there is no more weak acid. So what happens to any additional hydroxide?
It would stay as hydroxide.
What is it?
It would stay. As
Yeah,
hydroxide.
exactly. It would just stick around. So what we want to do is figure out, so at this endpoint, we will have consumed all of that sodium hydroxide, basically, because it will have reacted with the weak acid and then been converted to A-. Any additional hydroxide after that is just hydroxide. That's not going anywhere because there's no acid left to titrate it. So what we could do is just figure out how many moles of hydroxide are left over at that point. So we could just subtract 35 from 31, and that would be the number of excess mils. That'd be our volume of excess hydroxide. So that would be 3.75, 3.75 mils of basically just hydroxide with nothing to titrate it. So now, if we have a volume of hydroxide and a concentration of hydroxide, what can we figure out with that?
Molarity.
Not molarity, not yet. We can figure out molarity eventually, but what will just the concentration and the volume give me? What's concentration times volume?
Moles.
Moles, exactly, because it's just moles per liter times liters. That's moles. So we can figure out the number of moles of hydroxide that are left over. So that's 3.75 mils times 1 liter over 1,000 mils times 4.13 moles. 0.13 moles over liters. That cancels my liters, that cancels my mils, and that gives me moles of hydroxide. So how many, I don't think I have enough. I have a solar powered calculator here. I don't think I have enough light going on. Oh, looks like it's going to work. So 3.75. 0.413. So that gives me 0.00, don't fail. Come on, you can do this. 0.0015488 moles. That's how many moles of OH I have. How do I go from moles of hydroxide to pH? That's basically all I've got right now. I've got moles of hydroxide, and I need to figure out some way to convert that into a pH. How am I going to do that? Or let's go in steps. I have moles of hydroxide, and I have a volume. My volume is 25 mils of analyte plus 35 mils of hydroxide. So I've got 60 mils volume. So I've got a volume and I've got moles. What can I do with that?
Molarity.
I can figure out the molarity of hydroxide. Yeah, why don't I go ahead and do that? So that would be that number of moles divided by 0.060 liters. That's 60 milliliters. Come on. No.
0.02581 molarity.
0.025 what?
8125 molarity.
All right, that's
Where did the 0.060 liters come from?
that is 60 mils. That was my total volume.
Oh, yeah.
60 mils times 1 liter divided by 1,000 mils is that. So that gives us our concentration of hydroxide. How do I go from a concentration of hydroxide to a pH? Because you can.
Is that the anti-log?
What is that?
Is that the anti-log?
The anti-log of that will actually give you something. The anti-log of that will give you the POH. Because P just means anti-log. So if you took the anti-log of this, it would give you the POH. But we want the pH.
We can use the auto ionization of water formula.
Excellent, that's right. Now that we've gotten rid of all of our weak acid, there's still a weak acid left. And what is that weak acid? It's water. We always got water. And so water is a weak acid and a weak base. We know that it autoionizes into H plus and OH minus, and it does that all the time. And that is governed by a constant called Kw. That's an equilibrium constant because this reaction goes both directions and it's in equilibrium. If we have too much H plus and OH minus, it goes backwards and makes water. If there's very, very little H plus and OH minus, water will ionize and push it in the other direction. Well, what's happened here is that I have increased the concentration of OH minus. That's going to push the direction back to making water. And if I know what KW is equal to the concentration of H plus times the concentration of OH minus. That's how you figure out what an equilibrium constant is. You multiply the concentration of the products and you divide by the concentration of the reactants. But since the reactant is water and the concentration of water would be vastly more than the others, and it doesn't really change, we don't include it. So what is KW? What's the value of it?
One times 10 to the negative 14.
That's right. Great job. That means whenever I multiply the concentration of H plus in water and OH minus in water, I'm going to get that number. So if the amount of hydroxide ion goes up, the amount of H plus goes down. If the amount of H plus goes up, the amount of hydroxide goes down. So that whenever I multiply them together, I get 1 times 10 to the minus 14. So in this instance, we have our concentration of hydroxide. It's right here. That's my concentration of hydroxide. And so I can solve for the concentration of acid by plugging it into KW. KW equals 1 times 10 to the minus 14 equals the concentration of H plus times 0.02581 molar. So what's going to be my concentration of H plus? It's going to be small. Helps to have a scientific calculator for these. You can also use that website. Works as a scientific calculator. Because your answer is going to be in scientific notation because it's a very small number.
3.8740 times 10 to the negative 13.
Yeah, that sounds about right. Okay. So now I have my concentration of H plus. And if I have a concentration of H plus, I can figure out the pH. Because what is the pH?
Negative
Negative log what?
of hydroxide ion.
No. H.
Oh, I meant
H
hydrogen
plus.
ions.
Yeah,
H
hydro
plus.
H plus. So that's equal to minus log of that very small number. So that should be like 12 point something.
12.4.
What is it?
12.4.
12.4. Yeah, so you can see that the pH goes up radically. It goes up really fast once you've gone past the endpoint. Because the endpoint was when we had 31 mils of hydroxide. We just go like a little less than 3 mils over, and the pH goes from acidic to like 12. So that's how you do that. And the reason we do that, we don't use Henderson-Hasselbalch to figure this out, is because we no longer have an equilibrium between weak acid and the conjugate base, because at that point, there isn't any weak acid. It's all gone. So we don't have any. And so if you don't have any of something, you can't have an equilibrium. And so we're not in equilibrium circumstances anymore. So then we're not in this equilibrium circumstance anymore. So then we have to figure out basically what our concentration of OH minus is at that point. Okay. So man, that took a while. Yeah, there's a lot going on in just that one question. So is everyone clear on is there anything we need to review about this? There's a lot of like logs and stuff and everything.
Is this gonna be on the exam on Thursday?
It might. I can neither confirm nor deny. All right, so this was a question that you sent in, Vera. And so what was the issue you were having with it?
I guess because you guys were giving like two different numbers. I mean, I know you go from grams to moles
Mm-hmm.
to the mole ratio,
Right,
but because you gave numbers for hydrogen and oxygen,
right.
I guess that was what was confusing. I think my number ended up being something like 3.14 moles of water, but when I put it in, the answer is wrong. So
All right, so first thing to do is indeed convert both of these into moles. So if I have 50 grams of H2, how many moles is that? How do we figure that out?
1 mole of hydrogen over 2.00 grams of hydrogen gas.
Yeah, so 1 mole of hydrogen atoms is 1.008 grams. There's 2 atoms in a mole, so multiply this by 2. So that would be 2.016. So how many moles is that? All right. Hello?
24.80.
44.80 moles.
No, 24.
Oh, 24. Oh, right, 24. Moles of H2. Now, how many moles of O2 are we going to have?
1 mole of oxygen gas over 31.998 grams.
Right, so there's 2 atoms of oxygen in each mole of oxygen. So you need to multiply the molar mass of oxygen by 2. So how many moles is that?
3.125 moles.
Okay, so then we just use those numbers and figure out how much water would that make. So
Oh, I thought this was like a limiting.
it is. One of them is going to be limiting. Which one do you think is going to be limiting?
Looks like the hydrogen, I think. Sorry, I meant the oxygen.
Yeah, probably going to be the oxygen, right? So let's figure that out. So basically, you take moles of hydrogen. We multiply that by 2 moles of water for every 2 moles of H2. Oh, put multiplication over there. So obviously that would give us the same number. So if all the hydrogen was consumed, we would make, oops, we would make 24.80 moles of water. Now, on the other hand, we want to figure out how much water we would make if all the oxygen was consumed. So if all the oxygen is consumed, that's 2 moles of water over 1 mole of O2. So we'd make twice as much water, right? So that would be 6.25 moles, right?
Yeah.
Moles of water. H2, H2. So one of these is less. So the one that's less, that's how much you're going to make.
Okay,
So the O2 is limiting and the H2 is in excess.
okay, I get why I got it wrong. I put the answer as 3.125.
Mm. Right, but you get two for one.
Right,
Yeah, okay. And then the other question, we had a lot of them, but let's look at this one. So the question, this was on the review I posted on Chem 101. And so the question is, I got these 2 molecules. I've got A and I've got B. And the question is, constitutional isomers, basically, are they arranged in different order? Are the atoms put together in a different order? Are they cis-trans isomers in that around the double bond, we just have the constituents in the opposite place, or is it in fact just the same thing? Well, we can probably look and see whether it's the same thing first. So if it was the same thing, we should be able to just rotate B and it would look like A. And the question is, does it?
No.
It doesn't, right? Because this double bond is in a different place. That double bond would have to be give me another color. There we go. That double bond would have to be there for it to be the same molecule. So it's not the same molecule. So we can
I
get
can't
rid
hear
of
you, Professor.
we can get rid of that one. So let's look and see if they're cis-trans isomers of each other. So for that to be true, what's on this side of the double bond and what's on that side of the double bond should be the same for both of them. And let's see if that's true. So what do we have? So let's mark this 1 and 2, and I'll mark this 1 and 2. So actually I should mark them 3 and 4 just to make. So we know which one we're talking about. So what is around the double bond at carbon 1 here? What 2 groups do I have around the double bond of carbon 1?
Methane.
I've got a methyl group and I've got a hydrogen. Because remember, with skeletals, we don't include hydrogens unless we're looking at sometimes we put them for the methyl group, sometimes we don't. I kind of like doing that because it breaks, I don't know, just helps me. So actually we can eliminate this pretty quickly. So let's look at groups 3 and 4 over here. Does either one of them have a methyl group coming off of it?
Yeah, 3.
Just one?
doesn't both of them do?
Yeah, they're both. There's a methyl group here and a methyl group there. So it actually doesn't have a hydrogen. Carbon 3 is double bonded to another carbon and has a methyl group on one side and a methyl group on the other side. And what about carbon 4? Does carbon 4 just have a single methyl group? So let's look at carbon 4 here. Oops. So there's carbon 4. What are the two groups attached to carbon 4?
The methyl and
The
What-
what? Sorry, the what?
the methyl group, right?
It isn't a methyl group.
I thought CH3 was a methyl group.
It is, but that's not a methyl group attached to carbon 4. Why isn't it? What's
Oh,
there?
CH3, sorry,
What's there?
another carbon.
Another carbon. That's right. So that's not actually a methyl group. What is it?
Hydrogen.
It's a 2-carbon group. And what do we call a
Ethyl group.
2-carbon group?
Ethyl group.
Ethyl group, that's
Ethyl.
right. So it has an ethyl group and a hydrogen. So neither of these two carbons on molecule B have a single methyl group attached to either one of them, whereas this one does. So they're not cis-trans isomers either. So they're not the same molecule. They're not cis-trans isomers. They're constitutional or constructional isomers of each other. They're the same number of carbons, they're the same number of hydrogens, but they're put together in a different way.
Is that the same as, so there's 4 different types of isomers. There's constitutional, there's cis-trans, there's structural, and then there's
Structural and
stereo-
constitutional mean the same thing.
stereo isomers, I believe.
Constitutional and structural mean the same thing.
Oh, okay.
Yeah.
So there's 3 different types of isomers that we've
well,
learned so far.
Yeah, I mean, there's 2 different kinds of stereoisomers, but yeah, we'll just call them stereoisomers for now.
So for this one, they're the same because they have the same components. They're just arranged differently.
Oh, they're not the same molecule though. They have the same formula. They have the same formula, but they're not the same molecule. Just because
But that makes
2
them
molecules have the same formula does not mean they're the same. Yeah, they're isomers of each other.
Kind of related, I saw your lecture notes. Isn't that the same as that medication that was given for, I don't remember the name, but it was given to pregnant women to prevent morning sickness, but then,
Those were stereoisomers of each other.
oh, okay.
Yeah,
But
They
then
were-
it caused the birth defects.
they were stereoisomers of each other. And a stereoisomer just means that all of the atoms are connected in the same way, but they're different in 3-dimensional space.
Oh, okay.
That's the basic definition of a stereoisomer. So they're either above the plane in a ring, or above the plane in a double bond, or they have a chiral center with 4 different groups attached that you can't rearrange to look the same. Okay, so I have some other ones, but why don't you let me know what kind of questions you guys want to work on? You either put them in the chat. I don't want to spend time reviewing things you already know. So what sort of things would you like to review?
I had one from the lab, but I have to look for it.
Okay, what is it about? Or which lab is it?
I think it was the titration lab.
Mm-hmm.
It was. Let me see. Sorry, I have to pull it up to know exactly which one.
Because if it's a titration question, I have a titration question here.
Oh, it was just determining the pH
Okay, of what?
of the 2 milliliter buffer. So we had the Ka. Of
So that
the-
was, okay, so that was, that's where we had our pH 4.7 buffer, right?
Yes.
So we
Yes.
had equal volumes, 0.1 molar sodium acetate and 0.1 molar acetic acid. Right, we
Yeah.
put those two together
Uh-huh.
and then.
I
so
think I
what's
was
the-
thrown off because it
so
said
what's the
that.
question?
So it says, calculate the final pH of the undiluted buffer after 0.25 milliliters of 0.1 moles of NaOH is added. And it gives the Ka of CH3COOH is equal to 1.8 times 10 to the negative 5. And then we,
Yeah, I mean, this is basically exactly what we did
yeah,
to start. So, I'll
Yeah,
get you
yeah.
I'll get you started on it, okay?
no, I think that's why I wasn't sure which one it was, but I think I'd be okay because we just did that. I would rather we just move on to something
Okay,
else.
but yeah, just a couple quick things. Your final concentrations of acetate and acetic acid are going to be 50 millimolar. They're going to be half of these because you've added them in equal amount. So each one of them is going to be 0.05 molar. So from that, figure out how many mole, and then, so that's your concentration, and your volume is 0.002 liters. So figure out your number of moles of acetate and acetic acid. They'll be the same. And that goes to your ice table. That's the initial amount. So then the change will be, figure out how many moles of hydroxide that is. That is going to increase the number of moles of A minus and decrease the number of moles of HA. That's your change. So then at equilibrium, you will have less. Come on. There we go. So at equilibrium, you will have less A minus or more A minus and less HA. And so then you just do exactly the same thing. Moles of A minus over moles of A. There's your Ka. Figure out what the pKa is. It should be around 4.75 or so. And then you can figure out the pH from there. Okay.
Okay, thank you.
All right. No worries.
For the latest worksheet 10,
Mm-hmm.
so I was able to draw one promo for idobenzene, but I had a tricky time in terms of finding another name for it.
Oh, okay. Let's do that. So what's the name of the molecule?
1-bromo-4-idobenzene.
1-bromo-4-iodobenzene. Right. So for just the bare bones skeletal, we just go 1, 2, 3, 4, 5, 6. And you can either put the double bonds in there or you can just put a circle in there. Either one is correct. So 1-bromo-4-iodo. So that means we're going to have a bromine at the 1 position, And it doesn't matter which one you pick as the one position, whatever you pick, that's going to be one. So there's bromo. So that would be 1, and then 2, 3, 4, 5, 6. So you can see that 4 is directly across from it. So any molecule, you've got the bromine and the iodine straight across from each other is correct. And you're wondering what the other name is. Oops. Undo. Yeah. I have no hard time. No hard time tonight. There we go. All right. So there's my molecule. So you remember that when we have two substituents on benzene, we give them different names to tell what relationship they are to each other. Do you remember what those three were?
There's cis, trans, and I think you said,
That's for double bonds.
uh,
Is this the ortho,
Right. One is ortho,
para, and meta?
right? Ortho, para, and oso meta. Do you remember what they mean?
I think the ortho, I just remember those are the ones where it was like one on top of the other, like right next to each other.
Right. So ortho, they're right next to each other.
Uh-huh.
So if the iodine was there, they would be ortho to each other. And if they're two away from each other, so if I put the iodine here, so there'd be a carbon in between, what would I call that one?
That one's meta.
Mm-hmm. Oso meta. And then when they're opposite of each other, we call that para. So the other name for this would be para bromoiodo.
And these are the ones where you don't have to write
Benzene.
the para, meta, ortho. You can just put the letter.
You just put the P, yeah,
Okay.
P-O, P-M, or O. Or you can write it, either way is fine. So that's the other name we're looking for.
so like, for example, if this was on exam, you can write it either or, right?
Unless I ask for both.
Oh, that would be so mean. Okay.
Unless you have to answer both. But generally, that would be like an extra, if it was worth 10 points, I mean, this would be worth, 7, and that'll be worth 3 or something. But yeah, we're sort of looking for both.
Can we do the ones where you break down the reactant and product in that workshop? It's the next section,
Okay.
like for 2-methyl-1-pentene or pentene.
Oh, when they have water added to them?
It's the one where like you have to, so we draw the Lewis structure and then of the reactant and product.
Okay,
Where you have to break it down.
sure.
I was having a hard time figuring out where the breakdown was.
Oops. All right, let me find that. I was looking at that this afternoon. Okay. Yeah. Okay. There we go. So that was what question was that?
Number 6.
6.
Markovnikov.
Markovnikov, good old Markovnikov. Another genius Russian. so many important Russian chemists. So what does that refer to? Markovnikov's rule. What does that mean?
It's the addition of water.
Right. So actually, it's not just water. Water is the first one we learned about. But actually, Markovnikov figured out the rules of addition of a lot of things. But what we're learning about is water. Right. So water to being added to what exactly? What's the water being added to?
Alkene.
An alkene, right? It's being added to the double bond of an alkene. So the first thing we do is write the structure for that. So what is the longest stretch of carbons that includes the double bond that we can put in there? Because we know it's got a double bond because there's an ene at the end. Basically, we're looking for the root. What's the root of that molecule, of the name?
Propene.
Propene, right? The root is at the end. So the root is at the end. And then at the beginning, it tells us what are the substituents added to that. So the root is propene. So how many carbons is that?
3.
Yes. I still have trouble with propane and butane. It's one of those mental blocks. I've only been trying to remember it for like 40 years. Like just won't go in. So that's 1, 2, 3. And where's the double bond?
It's in the first.
Yeah, it doesn't really matter, right?
Yeah.
Because we either put it there and this becomes carbon 1, or we put it there and this becomes carbon 1. So it doesn't really matter where you put it. That's only true for propene. And where's my methyl group going?
In the second carbon.
On the second one. And let's just fill up the other hydrogens. That's just a CH3 there. So I could just, you can just put CH3 there if you want. And are there any hydrogens on carbon 2?
No.
No, because it's already making 4 bonds. So that carbon is all filled up. So what does Markovnikov's rule say? So that means we're adding water to this, right? We're taking a strong acid, like sulfuric acid, and water, and we're adding the water to that double bond. Does that mean like a whole water molecule gets added somewhere?
It's just OH.
Just OH? Where
And
does
hydrogen.
where does the other proton go?
Hydrogens pair up with more hydrogens.
So what two groups get attached to this molecule?
The methyl group and the.
I'm not adding a methyl group, I'm adding water. So where does the,
Oh, okay.
yeah, so I'm
you add
adding the
another
water
hydrogen.
here. So this is what I'm adding. And the question is, do I add like
Oh, okay. So
do I
like
add
the
a water
hydrogen-
to it, or what gets added to the
Yeah.
molecule?
You have to split it up. So
Yeah.
Right, it splits up.
add hydrogen to the first carbon
So hydrogen goes one place,
because it just goes on either
and the
side
OH
of the double bond.
hydroxyl group goes to another place. So Markovnikov came up with a rule to tell us which carbon gets the hydrogen and which carbon gets the hydroxyl group. So what's his rule?
So it's like the one that has the more hydrogens. That's where they go to, right? The hydrogen goes to more hydrogens, right?
Right. So the hydrogen goes to the carbons that has more hydrogens attached to it already.
So that'd be the first one.
So that would go to carbon 1. So we remove this double bond, because remember, we don't break both bonds. We just break the second one. And then the hydroxyl group goes to the carbon that has more carbons attached to it. And carbon 2 has 3 carbons attached to it. Carbon 1 only has 1 carbon attached to it. So that's where the hydroxyl group goes. So that is the Lewis structure of our product, right there. So the question is, what do we call that? And we really won't, you won't be tested on this until the next chapter, because this is anyone know what kind of a molecule this is?
It's an alcohol now.
It's an alcohol now, exactly, excellent. Yeah, we've added a hydroxyl group to it. Once you attach a hydroxyl group to a carbon, it becomes an alcohol. So this would be, we have 1, 2, 3 carbons. So this would be 2-methyl, 2-propanol. So we put an all, so we get rid of the ene and we put an all at the end. That tells you that it's an alcohol. And then the number directly in front of it tells you which carbon has the hydroxyl group. That's also isopropyl alcohol. Yeah.
So in this case for these ones, then it looks like it might be easier, instead of writing the CH3 at the end,
Mm-hmm.
to actually write out the whole thing. So then you can count how many hydrogens are already there.
I'm sorry, could you repeat that?
Because instead of writing CH3, because you know how you said we could do it shorthand,
Mm-hmm.
I'm wondering, is it better to break it down completely and write out all of the carbons and all the
Yeah, you can
hydrogens?
do it either way. So really the only way that would be different is that I would just have hydrogen, hydrogen, hydrogen. So that'd be the only difference. And then here I would have, see, that's why I like putting the CH3, because it gets a little complicated with all those bonds. So it gets a little messier. But if you want to do it that way, that's no problem with that. But it's the exact same molecule. But if that helps you visualize it better, then by all means, do it that way. Do you want to do the next one?
Yeah, so then whenever you do that, then you're getting rid of the double bond, because you said that's when it breaks, right? And then it splits into the water molecule.
Yep.
Okay.
Yep. So that, yeah, so what happens is, didn't really get into this, but there's two different, the double bond of a carbon, those bonds are not equal. There's actually two different kinds of bonds there. One is called, and if you take any additional chemistry, and I'm sure you're all going to become chemists, right? That's why you're taking this class. One of them is called a sigma bond, and that means that the electrons are directly between the two carbons. The other one is called a pi bond, and it's a weird bond, and it's because the electrons shared between the two carbons in a pi bond are up here and down here. So they're a lot more scattered. And so the pi bond is a lot weaker. And the electrons in that bond are a lot more accessible to other atoms because they're not right between the two atoms where it's really hard to get to them. They're up here and they're down here. They're farther away. So they're easier to remove. And so it's the pi bond that gets broken and the sigma bond stays present. That's why a double bond is weaker than two single bonds. Single bonds are always sigma bonds. And double bonds have additional pi bonds. A triple bond has one sigma in the middle and then two pi's. one above and one below. So just in case you need it more confusing. All right, so let's do this one. So pentene, I shampoo my hair with every morning. So how many carbons in pentene?
Is that 5?
5, right. So we go 1, 2, 3, 4, 5. And then where's the double bond?
You could put it in the first one.
Yeah, it's at 1. So
Here,
that's the very first one. So it's right there. And where is, are there any substituents?
Methyl group, and put that at the second carbon.
Okay. So then
So this
H.
one's kind of like the first one then.
Pretty much, yeah, exactly. And then H, 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 H. Okay, so again, carbon 2 is not going to have any hydrogens attached to it. So we add, so yeah, actually it's exactly the
It's
same.
exactly the same, yeah.
Yep, because we have a methyl at the 2 position and the first carbon has a double bond. So what'll happen, so where is the, who gets the H and who gets the hydroxyl group?
So same thing, the first carbon gets the hydrogen,
Yep.
and then the hydroxyl group is going to go to the second carbon,
And we're going to remove.
the double bond.
Now, the interesting thing is if you do number C, you should get the same answer.
But for that one, it's different because of the location, right?
Mhm.
That's the only thing that's
But it
different.
should make the same product.
Yeah,
Yeah, it should make the same product. This will already be CH3 and the double bond will be here. But then this carbon 2 will still be bound to more carbons than carbon 3. And so it'll look exactly the same.
and that's just because of where the location of the double bond is, right?
That has more to do with where the location of the methyl group is.
Oh, I see, okay.
If I put the double bond here, carbon 2 is bound to more carbons. If I put the double bond here, carbon 2 is still bound to more carbons. So it's still going to get the hydroxyl group regardless. So in that case, we've got 1, 2, 3, 4, 5. So that's pentanol. All. And the hydroxyl group is at 2. And the methyl group is at 2. So that would be 2 methyl, 2 pentanol. All right. Excellent job. All right, who's next? You just throw out a concept or something. We can make up something as we go.
So for that, for the Chem 101, where it's 1, 2, 3, 4, 5, 6, 7, 8 carbon with OH on carbon number 2. That's the end product for all single bonded, but you wanted us to draw the double bonded for it. So it's similar to what we're going through, but instead you want us to do a double bond. I just kind of wanted to be broken down to try to understand how to
Okay,
draw.
it's one of the Chem 101 problems.
Yeah.
Number
uh,
8, you said?
Number 23 for review for exam 2.
Oh, there it is. Number 23. Oh, okay. You draw it. Okay. So the product is this, so it's so that's the product, right? And the question is, what would you start with to get that?
It's a 8
Product.
carbon chain.
1, 2, 3, 4, 5, 6, 8. 1, 2, 3, 4, 5, 6, 8. Okay. Right. So basically, the question is, would you put the double bond there, or would you put, oops. Or would you put the double bond there? Those are basically your the two places you could put them. So which one of these would you have it at 1, 2, or 2, 3? There's 1, 2, 3, 4, 5, 6, 7, 8. So basically you try just putting them in both places and see where it would go. But it's got to be one of those two. So what would happen if we put it at the 1 position? So what's attached to the 1 position if we put a double bond there?
Two hydrogens.
Right. So we'd have a hydrogen here and a hydrogen there. And then we take this away. Oops. And what would hydrogen 2 have attached to it, or carbon 2 have attached to it?
Just 1 hydrogen.
Just 1 hydrogen. Right. So then if I was to do a hydration reaction there across the double bond, who would get the hydrogen and who would get the hydroxyl group?
The first one would get the hydrogen. The second
Right.
one would get the
Exactly.
oxygen. Okay.
So we would break this double bond. Oops. We would remove the entire molecule. There we go. We would remove the single. Oh, God damn it. We put the hydrogen there, and we would put the hydroxyl group there. So that would guarantee that the hydroxyl group went there. Now, if we put it in the other, if we put it at carbon 2 to carbon 3, how many hydrogens does carbon 3 get?
Just 1.
Just 1. Mm-hmm. So basically, then we've got a 50-50 chance of the hydroxyl group going there or going there. But if we absolutely wanted to make sure that it was attached to carbon 2, we would put the double bond there. So that's the answer. So that's what like synthetic chemists are doing all the time. When they're making something, they have to be very certain like where the the constituents are, because when they add something, they want to make sure that what they're adding goes to the exact place they want. So they wouldn't use the double bond, they wouldn't use the 2, what is that, octene? They wouldn't use 2 octene. They would use 1 octene to make absolutely certain that the hydroxyl group went there. They want to, leave no room for error.
So for something like that with the skeletal structure, we just write the hydrogen and the hydroxyl, just write the
Mhm.
letters.
Yep.
That's it.
Yeah. Basically, all you would do, you wouldn't have to draw any of the hydrogens. So all these would go away. And you just have, that's what the structure was. It just had a hydroxyl group here. That was it. So that would be the product. Mhm. And the starting material would just be that. Yeah, it saves you a lot of drawing. Okay, any other questions? Renee, you got anything for me?
Hold on, give me a minute.
Okay. Cassandra, you're always good for a little something. You got any concerns?
I'm sure I will, but I'm spending more time studying tomorrow as well. I'm just soaking up the knowledge.
Well, if you take too long, we're just gonna, if we just sit here staring at each other for 10 minutes, I'm just gonna turn off. Megan, how you doing? You got anything for me?
Right now, just trying to absorb everything. Oh man.
Just sponging.
Yeah,
Being a
trying.
sponge. There you go. Well, what I can do while you're waiting, I can put up what I put together and see if anything strikes your fancy. Here we go. So remember, still going to be responsible for intermolecular forces. So I figure this might be a good time to sort of quick. And everyone remembers these, I'm sure, with just love and admiration. So what are the different sorts of intermolecular forces? Do people remember what they are?
The London dispersion
Our
forces.
good old LDF. Mm-hmm.
Dipole.
Yep.
Hydrogen.
Dip. What's
Ion dipole.
ion dipole? That's a really good one.
Ionic.
Ionic.
And was the last one hydrogen bonding?
H bonding. There you go. So this is actually more of a well, I guess you could look at it as an intermolecular force. Generally, that's between atoms, but it can be between polyatomic ions as well. So that works. And this would be the strongest. Obviously, ionic bonds are very, very, very strong because you have charges. So what about these two? What sort of forces would they be attracted to?
Well, remember everything is LDF. because that's the lowest.
So how come we can't do dipoles? Don't these have dipoles, like one going this way and one going that way? Can't we get a dipole thing going?
No, because those are non-polar.
Excellent. Yeah, right. These are bond dipoles. That's important to remember. So with carbon dioxide, I've got a bond dipole pointing toward the oxygen because it's more electronegative. And I got another bond dipole pointing toward that oxygen because it's more electronegative. But when you add them together to make a molecular dipole, they cancel out because they're equivalent and they're symmetrical. So basically the only thing I can do is London dispersion force. Excellent job. What about B? Oops.
Ion dipole.
I got an ion, so that's telling me something. Where's my dipole? So yeah, I definitely have an ion here. Here's my ion. I keep trying to draw it. There's my ion. Where's my dipole?
Oxygen. The oxygen part.
So
Is that the one where like the charges are like moving towards the oxygen? Like I just remember.
right,
They're
exactly.
moving-
The
they're moving-
oxygen is more electronegative. And so it's pulling charge toward it, making it slightly negative, and the carbon's slightly positive. So I have a dipole pointing in that direction. And so since the oxygen is slightly negative, and this is a positively charged ion, that would be the interaction right there. And it would be an ion dipole. Great job. What about C? Now I've got two molecules that are the same. What sort of interaction could they do between them? And those are aldehydes. We'll learn about those. That's formaldehyde. We'll learn about that in the next chapter. It's quite a reactive molecule. So
Those are
two
dipole also, right? Because
They're dipole.
dipole, right. They each have a dipole pointing in the same direction. So the more positive part is going to line up with the more negative part. So basically they would this part would be pointing toward the carbon. They just sort of line up. Now, what about D? D is kind of a trick question.
that one's an ion dipole. 'Cause
Mm-hmm.
there's a negative charge on the oxygen on the second one.
Yeah.
And then it's also dipole too,
Mm-hmm.
because of they're moving towards the oxygen.
Yep. And if you're really, really on the ball, you would realize that this is a carboxylic acid. That is a weak conjugate base. And that in water, it would look like this. So if it looked like that, what else could you do?
H bond.
You could hydrogen bond, that's right. Because now I have a hydrogen bonded directly to an oxygen. So this makes this hydrogen very partially positively charged. And then I have my dipole over here, and then there's my H bond. So you get extra credit for that one. But yeah, dipole, and ion dipole, and a secret H bond. So got a gas problems. We've got
Can we do
limiting
practice with
reactant, percent yield. Yeah.
the conjugate acids and bases?
Mm-hmm.
Can we just
Oh, sure.
remember like how to identify them?
Sure. That was workshop 9 or workshop 8? 8. Oh, there it is. Yeah. I see it. Yeah, this one was tricky, huh?
Yeah, I think I get confused because especially how like you said, water can be a strong
Mhm. Yeah, it's
acid or
both.
base.
So
It's
can you see this? I can't tell if you can see. Can you see the acid base, conjugate acid base? Is it showing up on the screen?
No,
Oh, okay. Sorry. Oh, right, because I gotta share it first. There we go. Can you see it now?
yes.
All right. So, so basically you're given either the acid, the base, the conjugate acid, or the conjugate base. So what happens to the conjugate base, we know, goes with the acid. So what usually happens with the acid is that you add a proton to the acid, right? So if your conjugate base is A minus, that means that the acid must have been HA. And what usually happens to the base, it gets turned into a conjugate acid, usually with an increase in the charge. So the base going to acid generally has a charge removed, and a base going to a conjugate acid normally has a charge added. That's probably a little too confusing. Anyway, let's just have a look at this one. So here's our acid. And so acids generally lose a proton, right? And at least that's what our good Swedish friends thought. So what should the conjugate base be to this acid after it loses a proton?
So for that, you lose the hydrogen.
Mm-hmm. So if you lose an H plus, what do you have left?
Just the NO2.
And is that it? Just NO2?
It's gonna look different though,
Mm-hmm.
because now,
So it's lost an H plus, remember.
so now it has to have the opposite charge.
Now it has a minus charge, right? Because it was neutral before, but then it lost a positive charge. So it must have a minus or negative charge left over.
So does the 2 stay in a subscript like that?
Yeah, because that's the oxygen's not going anywhere. Remember, that's a polyatomic ion. That's a nitrate ion. So that stays together.
Because I think that's where I also was confused, because you see how like there's S at the bottom, like S 2 negative.
Mm-hmm.
That's the same thing as if you had like S subscript 2.
No,
No.
no.
Okay.
That is a sulfide ion. That is a single sulfur with a -2 charge. That is not the same as diatomic sulfur.
Okay.
So that's a single atom. The subscript means more than one atom. The superscript means charge.
Oh, okay. Yeah, I remember that now. Thank you.
Okay, there you go. So what's going to be my conjugate acid then? So if the base is water, basically the base is what accepts the proton. Oh, I put that in the
said you add,
So the proton went somewhere. Where did it go?
that went over to the conjugate acid. So the hydrogen,
So if this is remember, the conjugate acid goes with the base. The conjugate base goes with the acid. So if my base is H2O, the basics, so the acid donates a proton and the base accepts it. I can spell. There we go. So the acid donates a proton to the base. So if the base accepts a proton, what does it become?
H3.
H3O, right. And since we've added a positive charge to a neutral molecule, what's going to be the charge on it, on H3O?
It's going to be a positive charge.
That's right.
So it
And that's
has-
just hydronium ion.
Okay.
That's actually what H plus is in water. We don't have like just free H pluses floating around. It actually attaches itself to water and forms hydronium ion. So the overall equation is there's the acid, there's the base, there's the conjugate base, and there's the conjugate acid. So the conjugate means if it went in the opposite direction, this would be the acid donating the proton, and this would be the base accepting it if it went in the opposite direction. So you want to do the next one?
I
Or how
think
about the third or the fourth one? Because this one you can just write in here.
Sure.
Which one is the acid here? Which one is the base? Here we have ammonia, and here we have hydrogen cyanide. Ooh, nice. Who's donating a proton?
is it
Hydrogen cyanide or ammonia?
cyanide?
Yeah, the cyanide, hydrogen cyanide is. So that would be the acid. And it donates the proton to whom? Who's accepting the proton?
To the NH3.
NH3, right. That's why ammonia is a base. Ammonia is a base not because it forms hydroxide ions. I mean, it does. It forms hydroxide ions because it accepts a proton. And when it accepts a proton, if the only other acid around is water, it'll take the proton off of water. And when it takes the proton off of water, water then releases hydroxide, which is a base. So that's why ammonia is a base. But in this reaction, it's reacting with hydrogen cyanide. So what's the conjugate base to our ammonia?
Is that the CN negative?
Well, remember, the conjugate base did I say conjugate base or conjugate acid? I said
Conjugate.
conjugate base, didn't I?
Yeah.
I did. Now even I'm getting confused. Yes, that would be cyanide ion. Because it has lost a proton, H plus, and so what's left is the cyanide ion, Cn minus. You don't want that around. So that's the conjugate base. Who's the conjugate acid then? Conjugate acid would be whoever accepted the proton is now protonated.
So that's the NH4.
That's the NH4. What do we call that, by the way? It's something we learned early on. It's one of the polyatomic ions we've learned about.
Ammonia.
Ammonium, excellent, ammonium ion. H4 plus. There you go. Right, so just one more. You want to do the one with the sulfur on it? Because that one's a little confusing.
I think I'm okay. I just noticed, I think Dylan had a question about pH from moles. I think that's also something that's a little tricky too.
pH from moles.
Like when you're trying to I think it's a.
Now, let me check the chat.
version.
Figuring out pH from moles. Okay. Let's do a couple of examples. So if I have a 32.5 mils of a 0.1 molar HCl, and I add that to 500 mils of water, what will be the pH? So how would we go about answering this question? What's the first thing we need to do?
Find the molarity of water.
Water doesn't have a molarity.
Oh yeah.
Well, it does have a molarity. I think it's around, what is it? It's around 40 molar or something. Because water's 18 grams per mole. There's 1,000 grams in a liter. So it's 1,000 divided by 18. I don't know, it's high. But yeah, that doesn't matter. We need to figure out the final molarity in the water, but the molarity of what? What molarity do we need to figure out to get pH? We need the concentration of something to give us the pH.
Is it that?
Oh, HCl.
Not just HCl though.
Both of them, right? Wait, give me a second. Let me look at my notes.
Are we interested in the concentration of? So what happens when we put HCl in water? That's important.
Completely dissociates from hydrogen and chlorine ion.
Right, it completely dissociates. So we get H plus and Cl minus. Actually, we get H3O plus. So that is a strong acid. So that means it dissociates completely. If it was a weak acid, it'd be a lot. Actually, we can do a weak acid next.
This is the neutralization reactions.
The neutralization reaction would be HCl plus H2O gives you H3O plus Cl minus.
Oh, okay.
So that would be the neutralization. That's not a neutralization reaction. Neutralization reaction is H plus plus Cl minus. Yeah, because it's not a neutralization reaction. We're just diluting an acid. It's a neutralization reaction if we're adding an acid and a base together. In this instance, the base we're adding is water. So that water is now the base. That's the conjugate acid. Okay. So here's your acid. Here's your base. Here's your conjugate acid. There's your conjugate base.
I see. Okay, thank you.
All right. So clear all this out. 32.5. So mils of water. Okay, so what do we need to determine first? So we know that HCl is a strong acid. So any HCl I have is immediately going to get converted to H plus and Cl minus in solution. So if I have a 0.1 molar of HCl solution, it means I have 0.1 molar H plus and 0.1 molar chloride ions. But for the purpose of figuring out the pH, do I care what the concentration of chloride ions is?
No.
I do not, because it's a strong acid. So that reaction is not reversible. So I do not care what the concentration of Cl minus is. I am only interested in the concentration of H plus. Why am I only concentrate that? Man, losing my mind. Why am I only interested in the concentration of H plus?
Because in order to find the pH, like there's, because of the formula, it's like you have to have HA and like A minus, right?
Sorry, I couldn't quite make that out.
Because of like the formula, like to find pH, you have to find HA.
Not
like,
HA,
or A minus.
not A minus. Where do I get the pH from? We only use, I think the confusion is we only use the Henderson-Hasselbalch equation when we have a weak acid. This is only applicable when we have a weak acid. When we have a strong acid, the concentration of HA is 0.
Ooh.
So because there isn't any when I dissolve HCl and when I dilute HCl in water, there isn't any HCl. There's only H plus and Cl minus because it's a strong acid. So this doesn't apply because it's not in equilibrium. That only applies to weak acids. Now I have a strong acid. So in those situations, what's my pH equal to when I have a strong acid?
Negative log of H plus.
Exactly. Yeah, I am only interested in the concentration of H plus because the pKa is basically infinite. So it's just the concentration of H plus. So how am I going to figure out what the concentration of H plus is in this solution? Remember, I've got a strong acid and I'm diluting it into water. So how am I going to figure out what my concentration of H plus is?
For the reaction, because it dissociates completely, it would equal to the molarity of the HCl. So it's 0.1, right?
So my concentration is 1?
It would be the same. No, 0.1.
Oh, 0.1. That's right. 0.1 molar. So my concentration is 0.100 molar H plus. And what volume do I use?
Do we need liters for that?
Liters for what?
Since we're using molarity.
Right. So I need a volume. So what do I multiply this by? I think the confusion here is I have a concentration. But is that my final concentration?
No.
No, it isn't. So what would be the easiest way to figure out my final concentration? Oops.
Switch for the moles.
We can do it one of two ways. Yep, we can either determine the number of moles and then divide it by the volume. Let's do it that way, and then we'll do it the other way. So how many moles of H plus do I have?
is it the 0.1 moles over liter?
Mm-hmm. So I got moles on this side, but I have moles over liters on this side. They're not the same thing.
Multiply it by the volume.
Multiply by the volume, right? We got to multiply it by the volume. What's our volume?
0.0325 liters.
0.0325 liters, right? That's kind of sketchy at that side of the screen. So I have 0.00325 moles of H plus. But I need the concentration. I don't want the number of moles isn't going to help me. So how do what's my final concentration going to be? What do I multiply this by to give me a concentration?
Divided by 0.5 liters.
Nope. You're close. You're forgetting a little something though.
Yeah, you have to add the 32.5.
Yeah, you do. Right. So what's my final concentration? Moles over liters.
Wait, so is that 0.00325 divided by 0.
Mm-hmm. Well,
Divided by
multiplied
0.
by 1 over. Just so we have moles over liters.
Point 00610.
0.00610. So what is the log of 0.00610?
Two 2.21.
2.21. Is it 2.21 or minus 2.21? Just the log part. So the log of that is negative 2.21, right?
Yes.
Yeah. So the pH is plus 2.21. So that's how you would do that if it was a strong acid. If it's a strong acid, all we need to do is figure out the concentration of H plus. And it's straightforward. So the other way we could do it is just by doing CA equals VBCB.
Oh, that's what Dylan put in the chat.
Yeah, we could have done that. We could have figured out the concentration that way too. This also works for dilutions. And the reason it works for dilutions is because the moles of your concentrated stuff are going to equal the moles of your dilute stuff. So the volume goes up, the concentration goes down. And you can just figure it out that way. Now, let's do the same thing, but if it was a dilute, if it was a weak acid, because then it gets tricky. So let's say let's just do the same thing. I've got 32.5 mils of a 0.100 molar acetic acid this time. And then I dilute that with 500 mils of water. So now I have a different situation because I cannot just calculate H plus because this is an equilibrium. That is a weak acid. And in fact, this reaction is goes backwards more than it goes forwards. Because the Ka is small. Not as small as it is with water, 1 times 10 to the minus 14, but it's pretty small. It's like 1 times 10 to the minus 5 or so. So
So,
what do we do? What? Go
I
ahead.
just had a quick question. So,
Mhm.
you know, for strong acids or strong bases, there's no reversible.
No, that's what makes them strong.
Okay.
Is that the reaction only goes in one direction.
So in those cases, you could just do the negative log
Yeah,
to figure it
just
out.
figure out the concentration of H plus and you're done.
Okay.
This is a little more complicated because we have a weak acid. So we can't directly calculate the concentration of H plus. So what we're stuck with is figuring out what the concentration of the acetic acid is. And basically, if anyone can remember what the concentration of H plus is, that's what the concentration of acetic acid is going to be. What was our concentration of H plus? Well, we can just do it the V1, C1, V2, C2. So I've got 32.5 times 0.1 equals 532.5 times C2. So what's C2 going to be? Right, my new concentration. So it's my new dilute concentration of the acetic acid. You're going to make me do math. You people are terrible.
0.00610.
0.00610.
Yes.
Anything else?
32.
3. Okay. I just like to have at least, if I have 3 significant digits here, I like to carry at least 4. So that's my new concentration of acetic acid. Let's clear everything. So it's 0.00632, was it?
Yes.
Okay.
Oh,
So
sorry.
that's our
10.
Oh, one more 0?
After 1.
Oh, so it's 6103?
Mm-hmm.
Oh, okay. Six 1,032. That should be enough significant digits. Okay, so that's the only information I have. Now, if this was a strong acid, like I said, this would just go completely to H plus and acetate, and that would be by same concentration of H plus, and I could just do it exactly the same as I did before. But since this reaction goes in reverse, that makes it harder. And so this, we know the concentration of this, but we don't know the concentrations of either one of those. But what do we know? What is connecting the concentration of this and the concentration of these two things? There's something that connects those two things.
Is it the molarity?
Nope, but the molarity of acetic acid is related to the molarity of H plus and the molarity of acetate by what? There's something that relates those 3 things together. What is it? A ratio, one might say.
You mean like the pKa equation?
The
right?
pKa, exactly. So this is an equilibrium. So it is governed by the equilibrium constant. And what is the equilibrium constant? It is the concentration of H plus times the concentration of acetate divided by the concentration of HAC, the concentration of the acetic acid. That equals the Ka. What is the Ka for acetic acid? Well, we know what the pKa is. The pKa is 4.75. How do we go from the pKa to the Ka?
They aren't the same thing.
No. I can't just put this this is not equal to 4.75. The Ka is a very small number. Do you remember what the small p stands for? What does it stand for in pH?
The log.
Not
right?
log. You're close. The pH is equal to what log hydrogen concentration?
pH is negative log of
Minus log. Yeah, so the P stands for minus log. So we need the minus log of 4.75. That will give us the Ka, because the Ka is a really small number. It's a really small number because it's a weak acid. And if it's a weak acid, the Ka is low, meaning our concentration of H plus and acetate is going to be small compared to the concentration of acetic acid. And if you remember, I think it's around 1.8 times 10 to the minus 5, but we can, what's minus log 475?
negative 0.6766.
No, basically what I want is 10 to the minus 475.
Oh,
He said it's around 1.8 times 10 to the minus 5. I'd like it a little more accurate.
is it supposed to be a really small number?
Yep.
0.0000177783.
So 1778 times 10 to the minus 5. That's the actual Ka. The pKa is the minus log of that number. So now what do? Is I plug my concentration into that formula. So that means, oops, this is equal to the concentration of H plus and acetate over my concentration, 0.006132 molar. So I have this, I have this. So it's going to be my what's 1.778 times 10 to the minus 5 times that. can be a small number.
(1.09 times 10 to the -7, I believe.
Okay. So that means H plus and acetate, concentration of H plus and acetate is equal to that. Now, since the when acetic acid dissociates, it dissociates to H plus and acetate. So those two concentrations should be the same. So basically what we have is the concentration of H plus squared equals 1.09 times 10 to the -7. So what's the square root of 1 times 09 times 10 to the -7?
(1.1779 times 10 to the 14, -14).
No, you want the square root of that. Not,
Oh, my
don't want
bad.
to square it.
Professor,
Mm-hmm.
when do you think project to have this recording posted?
Tomorrow morning.
Okay,
Yeah, I'll put it up tomorrow morning.
I'm pretty lost on this one, to be honest.
Okay.
It's just,
This one is complicated.
yeah,
Yeah.
I think it's just, because I know you don't have as much space, but I'm
Yeah,
having
yeah. Once
trouble
you erase
following what you're
everything,
writing.
yeah, you go back to 0, right? Yeah.
3.301 times 10 to the 10 to the -4 power.
Into the -4, right? So we finally have our concentration of H plus, and so we just take 1 to the minus log of that, and we get the pH. So the pH would be a little bit less than 4, like 3.7 or something like that. And if you remember, when we did the titration of acetic acid, when they had a plot of the pH versus the amount of hydroxide added, notice that the pH didn't start at like 1 when we had just the acetic acid in it. It started at around 3, because that's what you're going to get for like a dilute acetic acid. You're going to get the pH of around 3 or 4. And then the pH goes up when you start adding base to it. So yeah, that one was a little complicated. Hopefully if you go over it a little more slowly, or if I do a better job explaining things. All right. Anything else, or people's brains on fire at this point? Sounds like people want to have a nap. Dylan's imploded. Oh, I'm sorry. Well, at least that's less of a mess to clean up.
Is the exam on Thursday through the Thursday Zoom link? Oh, I'm just kidding.
Yes.
Not via Zoom, is it?
Yes.
Well, is that where we
Yeah.
can find you if we?
That's where, no, actually, no, just use the office hours link.
Okay.
Yeah, everyone has that one. So yeah, I'll just be here on office hours on that link. And so you can ask me anything. during that time. So you can either email me or just go to Zoom. Okay.
Okay.
How
And
many
then following up,
questions-
I know we talked about this in our Wednesday lab like a few weeks back about Thanksgiving, about that week, and you said you would.
Oh, yeah, we're gonna cancel the labs on Thanksgiving.
Got it, Wednesday also, right?
Yep,
Thank you.
yep. Yep, yeah, that's, yeah. Everyone wants to, be traveling or getting vaccinated or whatever they are, doing both during that time.
Will it be a similar format in the last exam?
Yeah, there'll
Like the
be
amount of time in it?
10 multiple choice, and then followed by, I think, 5 longer, format questions, and an evil bonus at the end. The evil bonus will be something like this.
Oh, thank goodness, because if you had problems like this, I'd be like,
So we haven't done this before, so yeah, we haven't done like just the dilution of a weak acid. Yeah, generally we're given a concentration of either the acetate or the H plus, and then figure out the rest. But yeah, when you don't have either one, yeah, we haven't done that before. So it's a little more, you can see it's a little more complicated. That's why strong acids are much easier to work with.
I'm just wondering, so that 1.778 times 10 to the negative 5,
Mm-hmm.
or that was the log, that was the negative log?
Yeah. So the pKa of acetic acid is 4.75. Well, what does that mean? That means the Ka is 10 to the minus 4.75, because that's what P means. P means minus log of. So when you're going in the opposite, so when you're trying to figure out the pKa, you take the log and then you put a negative in front of it. When you're going the other way, when you're going from the pKa trying to get the Ka, then you're raising 10 to that power. You're not doing the log, you're doing the anti-log. The anti-log is 10 raised to minus 4.5. Because the minus log of 10 to the minus 4.75 is 4.75. So that's where this number comes from. That's 10 raised to the power of 4.75. So that's the Ka of acetic acid.
Oh, we're just inputting that into the calculator?
Mm-hmm. Yep. Yeah, and if you remember, what you were given, I think 1.8 times 10 to the minus 5 in the experiment, in the titration experiment, one of the post-lab questions, they gave you the Ka. So yeah, so we were just using a more accurate number.